Shortest distance between two skew lines. Welcome, everyone. Today we are going to explore a very interesting concept in three-dimensional geometry, the shortest distance between two skew lines. To start, let's define what we mean by skew lines. In a 2D plane, lines are either parallel or they eventually cross each other. However, once we move into 3D space, we encounter a third possibility. Skew lines are lines that are neither parallel nor intersecting. Now, you might wonder why they don't just meet. The reason is that skew lines are non-coplanar, meaning they do not lie in the same flat plane. Because they are essentially passing each other at different levels and different angles, they will never meet, but unlike parallel lines, they don't stay a constant distance apart either. Since they are constantly moving relative to one another, a natural question arises. How close do they actually get? The shortest distance we are looking for is the length of that one unique, specific line segment that connects the two lines and hits both of them at a perfect 90-degree angle. In other words, it is the length of the line segment that is perpendicular to both lines. In the next slide, we will look at the geometric setup and the vector equations we use to calculate this distance. Understanding the geometry. Now that we have defined what skew lines are, let's look at the geometry behind finding the distance between them. To find this shortest distance, our primary goal is to identify a specific direction that is perpendicular to both lines simultaneously. Think of it as finding the one unique path that hits both lines at a right angle. To do this mathematically, let's consider two lines, L1 and L2, represented by their vector equations. For the first line, L1, the position vector r equals a 1 plus lambda times b1. For the second line, L2, the position vector r equals a 2 plus mu times b2. Let's break down what these components actually represent. The vectors a 1 and a 2 are the position vectors for specific points, which we can call point S and point T, located on our first and second lines respectively. The vectors b1 and b2 are the direction vectors, which tell us the direction in which each line is traveling. And finally, the Greek letters lambda and mu are simply scalar parameters that allow us to move along the lines. Here is the key conceptual breakthrough. The shortest distance is actually the projection of the vector connecting our 2 points. That is, the vector SD, which is calculated as a 2 minus a 1, onto a vector that is perpendicular to both direction vectors, b1 and b2. In the next slide, I will show you the step-by-step derivation of how we use the cross product to actually find that perpendicular direction and turn this concept into a working formula. Step-by-step derivation of the formula. Now that we understand the geometric concept of the shortest distance from the previous slide, let's walk through the mathematical derivation step-by-step so you can see how we actually arrive at the formula. Step 1. Our first goal is to find a common perpendicular direction. As we discussed, the shortest path must be perpendicular to both lines. To find a vector that is perpendicular to both direction vector b1 and direction vector b2, we use the cross product. We'll call this normal vector n, where n equals the cross product of b1 and b2. Step 2. Once we have this perpendicular direction, we need to turn it into a unit vector, which we'll call n hat. A unit vector is essential because it gives us the direction without affecting the scale of our distance. To do this, we simply take our cross product from step 1 and divide it by its own magnitude. So, n hat equals the cross product of b1 and b2, all divided by the magnitude of the cross product of b1 and b2. Step 3. Now, here is the clever part. We need to find how much of the gap between our two lines lies along that perpendicular direction. We do this by projecting the vector connecting our 2 points, which is the vector SD, calculated as a 2 minus a 1, onto our unit vector n hat. The shortest distance, which we'll call d, is the absolute value of the dot product of a 2 minus a 1 and n hat. We use absolute value because distance must always be a positive value. Step 4. Finally, we can combine everything into one single, powerful formula. If we substitute the expression for n hat that we found in step 2 back into our equation from step 3, we get the final formula. The shortest distance d equals the absolute value of the dot product of the cross product of b1 and b2, with the vector a2 minus a1, all divided by the magnitude of the cross product of b1 and b2. This formula might look intimidating at first, but as you'll see in the next slide, it's actually a very logical progression of vector operations. We'll use a real-world analogy next to help solidify this intuition. Real-world analogy. Now, before we dive into the heavy calculations in the next slide, let's take a moment to step away from the abstract vectors and look at a real-world analogy to help you visualize what skew lines actually look like in 3D space. Imagine you are looking down at a radar screen at two airplanes flying through the sky. Airplane A is flying east at an altitude of 30,000 feet, while Airplane B is flying north at 35,000 feet. If you were to look at this from a bird's-eye view, essentially projecting their paths onto the ground, it might look like their flight paths are going to cross. However, because they are flying at different altitudes, they are not in the same plane, they will never actually collide. This is exactly what we mean when we say lines are non-coplanar. Now, think about the gap between them. The shortest distance between these two planes isn't just any random diagonal line. It is the length of the specific, straight line segment that connects them at the exact moment they are at their closest point to one another. Crucially, for this to be the shortest possible path, this connecting segment must be perpendicular to the flight path of Airplane A and also perpendicular to the flight path of Airplane B. This concept of a common perpendicular is the key to the entire formula we derived in the previous slide. Worked example. Here is our problem. We need to find the shortest distance between two lines. Let's call them line 1 and line 2. Line 1 is given by the vector equation r equals I plus j, plus lambda times the quantity I plus j plus k. Line 2 is given by the vector equation r equals 2I, plus mu times the quantity I minus j. To solve this, we will follow a systematic, step-by-step approach. In step 1, our first task is to extract the necessary vectors from these equations. Looking at line 1, our position vector a1 is I plus j, and our direction vector b1 is I plus j plus k. For line 2, our position vector a2 is simply 2I, and our direction vector b2 is I minus j. Next, in step 2, we need to find the vector connecting our 2 points, which is a2 minus a1. When we subtract I plus j from 2I, we are left with the vector I minus j. Now, moving to step 3, we need to find that common perpendicular direction we discussed earlier. We do this by calculating the cross product of our two direction vectors, b1 cross b2. We set this up using a 3x3 determinant with I, j, and k in the top row, followed by the components of b1 and b2. Expanding this determinant, we get I times 0 minus negative 1, minus j times 0 minus 1, plus k times negative 1 minus 1. This simplifies to our perpendicular vector, I plus j minus 2k. In step 4, we need the magnitude of this cross product. We take the square root of the sum of the squares of the components, the square root of 1 squared plus 1 squared plus negative 2 squared. This gives us the square root of 6. In step 5, we perform the dot product between our perpendicular vector and the vector we found in step 2. We take I plus j minus 2k and dot it with I minus j, multiplying the corresponding components. We get 1 times 1 plus 1 times negative 1 plus negative 2 times 0. This results in 1 minus 1 plus 0, which equals 0. Finally, in step 6, we apply our distance formula. We take the absolute value of 0 divided by the square root of 6, which simply results in a distance of 0. Now, look closely at this conclusion. Because our calculated shortest distance is exactly 0, it tells us something very important. These two lines are not actually skew. Since the distance between them is 0, it means the lines actually intersect at a single point. This is a great reminder to always check your final result, as we will discuss in our next slide on common mistakes. Now that we have derived the formula, let's put it into practice with a worked example to see how it actually functions in a calculation. Common mistakes to avoid. First, be very careful not to confuse the vector, A with the vector B. It is a very common mistake to swap the position vector with the direction vector. To keep this straight in your mind, just remember that A represents a specific point or a starting position on the line, whereas B represents the direction in which the line is moving. Second, never forget the absolute value. As we saw in our final formula, the result is enclosed in vertical bars. This is because distance is a physical magnitude and can never be negative. If your calculation results in a negative number, you have likely made a sign error, but always remember to apply the absolute value to ensure your final answer is positive. Third, pay close attention when calculating the cross product of B1 and B2. When using the determinant method, many students make a sign error, particularly with the J component. Remember that in the expansion of a 3x3 determinant, the middle term involving J is subtracted. Double-check that specific step carefully. Finally, do not simply assume that the lines you are given are skew. Always perform the calculation first. As we discovered in our worked example, if your final distance d equals 0, it means the lines are not actually skew, they actually intersect at a single point. Now that we have worked through the derivation and seen a practical example, I want to pause and discuss some common pitfalls. Even if you understand the formula, these small errors can lead to incorrect answers in your exams. Keep these points in mind as we wrap up with our final summary of the key takeaways. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear. First, let's revisit the definition of skew lines. As we discussed at the very beginning, these are lines in three-dimensional space that are neither parallel nor intersecting. They exist in different planes, which is why they never meet. Second, remember the concept of the common perpendicular. The most important geometric principle we use today is that the shortest path between these two skew lines is always a unique line segment that is perpendicular to both lines. If you can find that perpendicular direction, you've found the key to the distance. Third, let's look at our mathematical toolset. To solve these problems, you need to master two specific operations. We use the cross product of the two direction vectors to find that common perpendicular direction, and then we use the dot product to project the vector connecting our 2 points onto that perpendicular direction to find the actual length. Finally, let's look at our master formula one last time. The shortest distance, denoted as d, is equal to the absolute value of the quantity, the cross product of b sub 1 and b sub 2, dotted with the vector a sub 2 minus a sub 1, all divided by the magnitude of the cross product of b sub 1 and b sub 2. Keep this formula handy, and always remember to check if your distance results in 0, which, as we saw in our worked example, indicates that the lines actually intersect. Great job today!